If you have any questions, please use the chat. I do ask you guys all to stay on mute just to minimize any background noises. Please ask questions in the chat and we will get through them throughout the presentation. I'm going to turn it over to John Holz, who will present himself and introduce the speakers and will give this presentation. Thanks, John.
Great, thank you. And thanks for everyone joining us this afternoon. I think I got the dog locked up and the doorbell shut off, so Amazon shouldn't be interrupting us today. We're going to be sharing some thoughts on successful lake management, and we're also going to attempt to tie in some discussion on the use of alum to improve water quality by controlling internal phosphorus loading. I'm going to be doing most of the speaking today. Bill James and Tad Barrow will also be unmuted so they can speak as well. Before we get started, a big thank you to the Illinois Lake Management Association and Lake County Health Department, specifically Alana. We've been attending these conferences for a number of years now. We've gotten to know the staff at Lake County. They really do a good job there. I encourage everyone to visit their website. There's some great lake management resources there. Over the years, there's been, I guess, an interest in kind of hearing our presentation on a systematic approach to lake management, as well as a lot of interest regionally in Lake County, Illinois, on the use of alum. So we were invited to give this webinar, and it got shared widely, so we certainly have more people on here than just from Illinois today. This is a little outline of what we're going to talk about. I'll go through some quick introductions, background on water quality issues and causes, just so we all understand what we're here talking about, nutrient sources in lakes, the systematic approach to lake management, and then we're going to make a somewhat awkward transition, but a transition into using alum as a tool in lake management. And we'll end with a cool alum case study that Bill James did the research on at Long Lake, Wisconsin. We miss you pre-COVID, John, and so does the person who used to cut my hair, but that's me. I'm a former professor at the University of Nebraska. I'm a limnologist by training. I taught limnology and lake restoration courses at Nebraska. We ran, along with Tad Barrow, we ran a successful research and extension program there. We focused a lot on water quality improvement techniques and did a fair amount of research for EPA. Along the way, we were doing some testing on alum. We kind of moved that along in terms of dosing and application techniques. And about 10 years ago, Ted and I left the university and started working at HAB Aquatic Solutions full time. We're also grateful that Bill agreed to join us. Bill was a director for the Center of Limnological Research and Rehabilitation at the University of Wisconsin Stout. In addition to being a director there, he's a research limnologist and instructor. Over the last 40 years of his career, he's done a lot of neat and interesting things, but his current interest is on the use of alum to control internal loading in lakes. And Tad Barrow, he's the B in HAB. His background is in fisheries. Tad and I met a long time ago playing pickup basketball at the university. We didn't really like each other at first, but we went on to do a lot of research together and eventually founded HAB. Tad's background is in extension. A lot of you are familiar with your state's algal toxin alert system. Tad was influential in establishing that at a lot of states early on. The problem we're here to talk about, pretty easy to understand, poor water quality in lakes. I would argue that poor water quality in lakes has many symptoms, but most of those symptoms are somehow associated with excessive algal growth. Excessive macrophyte growth would be one that maybe isn't. Invasive species may be another that isn't. But a lot of things that we are concerned about in terms of poor water quality in lakes are somehow associated back to having nuisance or excessive amounts of algae in the lake. This excessive algae, if you get enough of or the wrong kind of the algae, can produce algal toxins, which create human health concern. We can get low clarity, the lake stinks, and we can easily even get indirectly, we can get low oxygen conditions caused by having too much algae in the lake. All that organic matter eventually sinks, goes down to the bottom, and as it decomposes, that process removes oxygen from the water column. Potential fish kills certainly come into play if the water quality gets bad enough. And the one that brings a lot of us to the table is reduced recreational and property values. When I was in graduate school, my major advisor avoided any talks of economics. He was not comfortable mixing science and economics. Over the years, I've come to think that maybe it's okay. And I think we can learn a lot by mixing the two at times. So property values, that's certainly a driver for some to improve their water quality. There's been a number of good studies and more studies coming out all the time. Probably the largest study that I'm aware of was a study in Minnesota where they examined over 1,200 residential property sales at lakes, 37 different lakes from 1966 to 2001. And they correlated the sale, the amount that the property sold for with the clarity of the lake. And they found a significant relationship. You pull one lake out of that data set, Leech Lake, for example, they found that if the water quality at Leech Lake increased by 3 feet, the property value increased by $509 per foot, or about $24,000 on a 40-foot lakefront lot, so a relatively small lot. I did update these dollars to current dollars recently. The interesting thing that I always found in that study is that you were penalized more for a decrease in clarity. So a 3-foot decrease in clarity led to a $700 per frontage foot decline in property value, or about a $28,000 decline on that same lot size. So we see this. This is a real phenomenon. Real estate agents call us. They want to know what lakes we've been to, what lakes we're going to. They want to know if we have a water quality data set. So people are tuned into this property value lake water quality issue. A more recent study was done in northern Wisconsin. They looked at 324 recent property sales. And there was a range, but about 3 to 16% increase in home value with that 3-foot increase in water clarity. So the average home in that study was $243,000 value, and that increased by about $26,000 with every 3-foot increase. And that's about what we see. There are some other studies out there. I sat in on an EPA webinar recently, and then there's some kind of unpublished studies, but we see somewhere in that 10 to 20% increase with improvement in water quality. More extreme example would be a study at Ohio State, at Buckeye Lake just outside of Columbus, and that lake has had significant toxic algae problems for years, and the real estate there is high dollar. So over a 6-year period, they lost over $100 million in home values due to algal toxins. More recently, these are just some of my own observations during and post-COVID. We are definitely seeing increased pressure on our water resources during and after COVID. Most in Alberta, 30% increase in fishing license sales over the last year. Iowa is about 25% increase. Most states I talk to are in that 20 to 40% increase in fishing license sales. If any of you have tried to buy a boat, an RV, a motorcycle, an ATV, a lake home property, all of that, you're finding that they're becoming more expensive and harder to find. We're seeing an economic shift in spending patterns. People aren't recreating in Cancun. They're recreating in Wisconsin or Illinois or where in their backyard. We're paying more attention to these resources and perhaps maybe more willing to invest into the quality of them. Property values are probably going to increase with that pressure. That provides some tax-based growth opportunities and perhaps some increased public health responsibilities as more lake users may be demanding safer water. So that's just something, my own kind of own observations, but I believe this is real. We're starting to see this. I know our company, for example, we've had more calls since last summer, more calls and emails and interest in water quality since last summer than we ever have. So back to the symptoms of poor water quality. The cause in general in fresh water is phosphorus. We've known for a long time, since Willenbeter and before published this relationship in 1968, where we're looking at increased phosphorus loading along the x-axis and the algae response along the y-axis. Just an aside here, you're going to hear me talking about chlorophyll a lot today. Chlorophyll is a light harvesting pigment. The green pigment in plants is also found in algae. So we can go into lake water and lyse the algal cells with alcohol and measure essentially how green it is. So the more chlorophyll in the water, that's really just a measure of how much algae is in the water. So higher chlorophyll means more algae. So and this was a study of lakes all across the world. As you increase phosphorus, you increase the amount of algae in the lake. And that's pretty typical for freshwater systems. In marine systems, it tends to be nitrogen that drives the productivity, but in freshwater lakes and streams, it tends to be phosphorus. But there's a little bit more to the story. As we increase in trophic state or phosphorus concentration in a lake, we not only increase the amount of algae or the amount of chlorophyll, but when we get to a certain phosphorus level or a certain productivity level, we oftentimes experience a shift from what we may call it, some of us may refer to as good algae or desirable algae, and those might be algae like greens or diatoms. But when we get a lot of phosphorus, we get a shift toward cyanobacteria or blue-green algae, and those are the scum forming, bloom forming, toxic forming. So not only do we get more algae with phosphorus increases, we can also get the wrong kind of algae. So in my mind, a pretty logical next step is to ask the question, well, if a lot of the problems we're seeing in lakes is associated with having too much phosphorus and too much algae, seems to me a logical question is, well, where's this phosphorus coming from? And it is a logical question, but unfortunately, I think sometimes it's overlooked. Identifying the phosphorus sources is key to successful lake management. We know that high phosphorus leads to these excessive algae, and the associated water quality issues. But if we don't understand where that phosphorus is coming from, it makes it very difficult to manage it. We need to understand the source. This cartoon is so simple that sometimes I think me showing it might offend some people, but I'm actually surprised sometimes by how much this is overlooked. All this cartoon is doing is saying we can get external sources of phosphorus. That's phosphorus that comes from outside of the lake, watershed loading, waterfowl, atmospheric deposition, runoff, stormwater, all those things where the phosphorus originates from outside of the lake. But then we also have internal sources of phosphorus, and those tend to be the bottom sediments. They're full of phosphorus, either naturally occurring, or it may be phosphorus that's deposited in the lake from the watershed. But that phosphorus can release or recycle that phosphorus back into the water column. So we need to understand both sources and the relative contribution to successfully manage a lake. External sources of phosphorus, these are probably the ones that most everyone would be able to name and be familiar with. Just put up a few examples here. Septic systems, agricultural runoff, lawn fertilizers, stormwater, waterfowl, atmospheric deposition, all those things that most of us could probably list pretty easily. Internal sources of phosphorus are perhaps a little less known, but what we're referring to here is the mobilization of phosphorus from the bottom sediment into the overlying water for the algae to use. And that can happen by diffusion. So the chemistry of the sediments, we'll get into a pretty detailed discussion of that later. It can also happen as ridded macrophytes or plants in the lake uptake phosphorus from the sediments, eventually die, decompose, and release that phosphorus. Or it can happen by the activity of rough fish. For example, carp, as they root around in the bottom sediments as they feed, they can disturb the bottom sediments and then introduce some phosphorus back into the water column. We're not going to spend a lot of time talking about the last two bullets on this list here today. We're going to mainly talk about diffusion. The carp and carp management could be a whole nother presentation for another day. So one thing I did want to mention back to this slide. So historically, we as lake managers haven't paid as much attention, I would argue, in internal loading. And I've certainly seen a lot more attention being paid to internal loading sources of phosphorus, I would say, over the last 15, maybe 20 years of my career. Some of that is we know more about it. We're doing more research on it. We measure it, we look for it. So some of it is maybe it's always been there and we didn't pay that much attention to it. But some of it might be that it's becoming more important. As our lakes accumulate watershed phosphorus, we're accumulating more phosphorus in the sediment, which could increase internal loading. So some of our systems might be reaching a bit of a tipping point where the sediments are overloaded to the point where they're now an important contributor to the water column phosphorus concentrations. The other things that might be going on, lake warming, for example, could increase this phenomenon as we have longer ice-free periods, longer growing periods, longer anoxic periods in lakes, which also could increase internal loading. So I'm going to talk a little bit now about some key steps in lake management, and there's really nothing magical about these steps. Sometimes I think there's 6 steps, sometimes I think there's 8 steps, sometimes I think some of these steps should be combined. I've seen other people have their 7 steps. So there's really nothing magic about this. It's just really a way to frame my thoughts, frame my view of lake management, and preach, if you will, the importance of a systematic approach to lake management. Data-driven, proven solutions, not skipping to implementation without doing the diagnostic and feasibility, reducing our risk and uncertainty, and improving our chance of success. So here are the 7 steps. Again, I change them all the time, change the wording, nothing magical here, but we're just kind of go through these quickly. Problem definition, we need to figure out what the problem is. Everyone needs to agree with that. What are we trying to fix? What do we want it to look like? What are the goals? We need to understand where this phosphorus is coming from. So we're going to talk a little bit about water budgets and phosphorus mass balance. Help us understand how much is coming from the watershed, how much is coming from within the lake, so we can design appropriate solutions. Once we build a model, now we have a cool toy to play with. We can ask some what if questions. Well, what if we turn this knob down, decrease this phosphorus contribution? What happens to the amount of algae in the lake? So we can play some what if scenarios and increase our opportunity for success. We can write everything down, put it in a plan, increase our chance for accountability. We can look at different alternatives, how effective they're going to be, and look at their cost effectiveness. How much bang for the buck are you getting for the different alternatives? Number 6, this is the one that everyone likes. This is the one that everyone wants to jump to. I always say we all have a brother-in-law or an uncle that knows exactly how to fix the lake. And I never hear the brother-in-law or the uncle talk about steps 1 through 5. They talk about step 6. Everyone wants to jump into doing something. Let's implement the solution. Let's do whatever, X, Y, Z. But have we done the appropriate steps? Have we let the science tell us the answer? Have we reduced our risk and uncertainty and made sure we're spending those resources wisely? The 7th one, no one likes to do either. No one likes to fund it, but we need to monitor after we implement our plan. Is it working? What's working good? What's not working? What do we need to tweak? What do we need to quit doing? What do we need to do more of? Problem 1, I realize I can't read the top of my screen the way the Zoom is here, but I think I remember what it says. It's just really a review of everything we know about the lake. You know, what's the phosphorus? What's the chlorophyll? Are there any water quality standards? Let's ask the lake users what they think of the lake, what the problem is. What are the algal species, toxins? What are some of the watershed attributes, land use, things like that? What's available? When I was putting this slide together, it reminded me of an exam question I used to ask my students in limnology. I used to ask them, if you were a lake manager and you could only know 5 things about the lake that you had to manage, what would they be and why? So those of you that are getting bored, you can think about that question as we move along here. I would argue the first 3 are easy, and then the discussion happens. Step number 2, we need to understand some type of a mass balance for the nutrients. And if we're focused on phosphorus, it's going to be a phosphorus mass balance. What's coming into the lake, what's going out of the lake, where it's coming from, and how much is coming from each source. And I would also argue that sometimes we need to know what time of the year. Oftentimes we do an annual mass balance, but I've worked on lakes before where on an annual budget, only 25% of the phosphorus is coming from an internal source. But if you look at the summertime when the algae are blooming, 90% of the phosphorus is coming from an internal source. So sometimes we need to look at seasonality. So really you need a good water budget. You need to understand the water inflow and outflow of the lake, how much is being stored in the lake. And then we can apply a nutrient concentration to those sources to come up with a load. So we have an external load and internal load. Some of that is being deposited back into the sediments. Some of it's leaving the lake and some of it's being stored. So here's an example of Bone Lake in Wisconsin where they did this on an annual basis. And they found that they're getting 45% from their watershed. So external loading, about 15% internal load, 11% from surface precipitation and atmospheric deposition, septic systems, and two creeks and tributaries that are coming into the lake. CLP here, that's curly leaf pondweed. So we talked about that being another internal source. So this is a type of plant that's uptaking phosphorus, dying, decomposing, and releasing phosphorus back into the water column. So this gives us at least an initial roadmap of where we would focus our efforts on managing this system. I would argue that skipping this step and not coming up with this type of a roadmap and going straight into implementing a solution is guessing. It may be an educated guess. It may be a guess based on recent or past lake management. And it might not be too bad of a guess, but at some degree, it's a little bit of a guess because you haven't really done the diagnostic and feasibility. Now we have the model and we have a cool toy. We can start asking these what if questions. So if we have a lake where the current phosphorus concentration is 70 micrograms per liter, and we want it to be 40, Well, what happens if we
Hey, John, this is Alana. Sorry. Just sometimes the audio is going in and out a little bit. Just stay close to your computer.
Okay.
Yeah, thank you.
So we can start to ask what if questions. So if we have a current phosphorus concentration of 70 and our goal is 40, what happens if we work on internal loading control? Well, in this case, the model is telling us we could meet our goal. We could meet our goal with chlorophyll, and we could also increase water clarity. So we can begin to ask those questions on tweaking different components of the model and looking at the predicted outcomes. Develop a plan. This is off Lake County's website. They have a good resource on there on lake management planning guidance. Everyone's lake management plan looks a little bit different, but in general, you identify who needs to be involved. You need to review the lake background, define the problem, the data review, the modeling, the results, establish goals so you know what you're trying to achieve and can establish some accountability. Most management plans will screen and evaluate potential solutions, what might make sense given, for example, your mass balance, for example. And a lot of them will recommend a list of solutions that are at least feasible, that have a chance of working in this lake, and oftentimes identify funding sources. Some management plans will also go a little bit further and actually evaluate these alternatives or feasible solutions, rank them, look at a cost analysis, how much bang for the buck are you getting them. Other lake management plans will leave that out and make that part of the phase 2 of the management program. Alternative and cost analysis is really just taking that list of things that might work. Here's some work that was done by Joe Bischoff in Minneapolis, where different project types were lumped together into broad categories, and they looked at how much it would cost to remove a pound of phosphorus from the system. Some practices, like some watershed BMP, were pretty expensive, $6,000–7,000 to remove every pound of phosphorus, and other solutions were a lot more cost effective. And here you can see Alum was one of them for internal load control. So we can start looking at bang for your buck. Here's a project that I was involved in Carter Lake, Omaha, along with the current group of fire engineering in Omaha. And this work was highlighted in Nolms's Lakeline magazine. And here we were taking that list of feasible solutions. We had a load reduction goal where we wanted to remove 974 pounds of phosphorus from the annual budget. And we started stacking up different solutions, their predicted load reduction until we got to the goal. And we started looking at which ones were the most cost effective. This was a big project, a $6 million project, but the approach was the same. Finally, step 6, we get to do something. This is where you get to execute your plan, finish the design, and implement the management practices. And then the monitoring. I think I already talked about the importance of this. It allows you to adapt. Not everything's going to work as the model predicted. What do you need to do less of? What do you need to do more of? And how can you shift around your approach to maximize the cost effectiveness? We're going to shift from that kind of lake management planning and structure into the second part of what we were invited to talk about, and that's controlling one component of the budget of the mass balance with aluminum salts or alum. To understand that discussion, we need to dive in a little deeper to understand how phosphorus moves from the lake sediments to that overlying water. So the first thing that I want to highlight, very important here, is phosphorus in lake sediments is tightly bound to iron under aerobic conditions. So that is in the presence of oxygen, phosphorus stays very tightly bound to iron. Phosphorus can be bound to many different things in the lake sediment, aluminum, calcium. It can be free, it can be bound up in organics, but it can also be bound to iron. And we're particularly concerned about that because that bond is not very stable in a lake in a lake environment, because when those lake sediments go anaerobic or they lose the oxygen concentration goes to very low or to zero or near zero, the iron bond, the iron phosphorus bond is broken and the phosphorus is released into the overlying water column. This is the diffusive internal phosphorus loading. Okay, so in a lake, a lot of lakes will stratify thermally, where we have the warm, less dense water floating on top of the colder, more dense water, and it creates two zones with different densities, and there's a resistance for this upper zone and bottom zone to mix. So throughout the summer, this bottom zone can remain somewhat isolated. And in this case, in the bottom panel here, we're looking at dissolved oxygen. And this line here that I'm tracing is the 1 milligram per liter line. And so everything below that is very low oxygen. So the bottom 4 to 12 meters in this lake has no or very low oxygen. So in a situation like this, the iron is going to be releasing the phosphorus, and we would anticipate high internal load of phosphorus, and that phosphorus accumulating in this deeper unmixed water we call the hypomylium. Eventually, that water can get transported to the surface for the algae to use. And that can happen as in this case, the thermocline deepens and trains some of that water, or we have a wind mixing event that brings some of that up, or some algae can actually migrate and go down into this phosphorus-rich water and utilize it. The important take-home point from this slide is to understand this phosphorus-iron bond, and it's how it's regulated by the oxygen concentration. Here's some data that Bill collected at a lake in Wisconsin, North Pike Lake. So the brown in this upper diagram is the sediment. And here we're looking at phosphorus concentration in the sediment pore water. So think of that as the pore water. That's the water that's between the sediment particles. And we can go in there and measure that phosphorus concentration. And when we do that, we typically find that it's very, very high in the sediments. But as it gets closer to the sediment water interface, it decreases as that phosphorus is released or leaves the sediment and goes into the water. So that's internal loading is what the diagram is showing there. Here, Bill actually went out and measured it. So 0 here is the water sediment interface, and he's going down into the lake bottom 9 centimeters at a bunch of different dates throughout the year. And what you see here, the top 4 centimeters, very low pore water phosphorus. So this top 4 centimeters, the phosphorus in the pore water is being released, most likely from the iron, leaving the sediment, going into the water eventually for the algae to use. As we go down deeper, we see higher concentrations of the sediment pore water. So this phosphorus in this pore water at depths 4 through 9 centimeters is not contributing to the internal loading. And that's common in lake sediments. Most of the phosphorus action is in that top, I would say 4 to 10 centimeters. This is what I was talking about earlier. There are some types of algae that can regulate their buoyancy, either by either they're motile or they can also just sink down or float back up. And so some of them will hold a daytime position in the upper water column and photosynthesize there. But at night, when they're not using the sunlight, they'll go down to darker waters where the phosphorus concentration might be higher, uptake the phosphorus and move back up into the day, move back up during the daytime. So that's another way we can move phosphorus from deeper water to shallower water in the summertime. So what are the consequences of this internal loading? Let's focus over here on Cedar Lake. So the top panel here is the chlorophyll. We're looking at 2010 from May through October. Starts out lower, increases till we get toward the end of the summer, and in the fall we see the largest blooms. Well, when we look at the dissolved oxygen at Cedar Lake, we find that it's going anoxic in the bottom few meters of Cedar Lake. That's this white blob here. And at that same time, we're seeing the algae increase as they're able to utilize that phosphorus source. And then at the end of the summer, beginning of the fall, we have complete mixing, bringing that phosphorus up to the surface at higher concentrations, and we get bigger algal blooms. So that's really the consequence of the internal loading, is that it eventually makes its way up to the surface and can fuel this poor water quality in the form of nuisance algae. So on to sediment phosphorus inactivation. That's a method or one tool to address this internal phosphorus loading. And again, I stress the use of alum or sediment phosphorus inactivation is a tool. It's not always appropriate for every lake. I'll never forget, we were just starting an alum application project on one of Bill's lakes. And it was kind of a high profile project, and they wanted to have a media day and also invite all the homeowners and just have a little education session on the shoreline about what we were getting ready to do, how alum worked, discussion of internal loading, and just an overview of what we were about ready to do. And Bill was there, and those of you know Bill will get a kick out of this story. Bill spoke first, and the first thing he says to the media is, well, alum doesn't always work. And I cringed a little bit. Maybe that's not the first thing we wanted to tell the media, because that's what they picked up on. But he's right. It doesn't always work. It's just a tool. It's not the silver bullet. It's to be utilized for a specific purpose. Our company has done about 120 lake alum applications now, and we turn them down. We're not going to be doing this in lakes where it's not appropriate. So that's why we need to do the feasibility study. So back to the alum application, it's applied using specialized equipment and application technology. It's important to do it right. You need to get mixing of the alum with the lake water. You need to put it in the precise location. You need to maximize the flock formation and the settling to get it down to the sediments. It's somewhat of a holistic approach, I think you could consider. We're addressing that internal load. It complements external phosphorus reduction efforts in the watershed. Watershed and external load control is extremely important. Internal load control just works alongside with that. It doesn't replace it. Aluminum sulfate, or the trade name is alum, you'll hear referred to as alum. We precisely apply that to the lake. It mixes with the lake water. Alum is applied in the liquid form. It mixes with the lake water to form a precipitate or a flock. That flock is what has the binding sites on it to attach to the phosphorus to attach to. The flock settles down to the bottom, and these unfilled binding sites are delivered to the phosphorus-rich sediment to intercept future sediment phosphorus release. So the idea here is, remember that we were discussing how the iron phosphorus bond was unstable, and iron released phosphorus when there's no oxygen. Well, it turns out that the aluminum phosphorus bond is stable. So if we can force the phosphorus off of the iron onto the aluminum, we don't have to worry about it releasing when there's no oxygen. So that's really quite simply what an alum treatment does, is it supplements the amount of aluminum that's already in the sediments and forces the phosphorus off of the iron onto the aluminum so we don't have internal loading events. So the flock that forms here, that's this white milky looking substance behind the barge, that sinks pretty quickly. It's an aluminum hydroxide flock. It binds with the phosphorus to form an aluminum phosphate complex that's very stable in a lake environment. It's not sensitive to these low oxygen conditions. It settles rapidly. It puts a thin layer on the bottom sediments, maybe an inch thick, that quickly becomes incorporated into the sediments. You don't see it. That's what you want. The sediment stabilizes it in place, and those unfilled binding sites on the flock are then there to intercept future internal loading, that is phosphorus coming off the iron. I'm going to see if I can get this to play. Rod Zizette with Herrera took some underwater video after our alum application at Green Lake in Washington in 2016. There's nothing real fancy about this. He had a GoPro on a pole, and this was about a day after the application, and he just ran the GoPro through some shallow water, and this gives you an idea what the flock looks like. That's the white substance you see on the bottom and hung up on the lily pads. That's the flock. It kind of looks like snow, settles down, evenly coats the sediment. Now you have this barrier there to intercept phosphorus as it's released. You'll see some of the flock is on the plants, that gets knocked off, settles down to the bottom with time. Thanks to Rob for sharing that video. So a little bit more on how it works. If we look at a profile of the lake sediments, so this 0 is the water sediment interface, and we go down in depth and we can measure this. What we have, I guess I should start over here to the left. We have all these different forms of phosphorus in the sediment. It can be dissolved, it can be iron bound, aluminum bound, calcium bound, and it can occur as organics. So this redox P, so the stuff here in the orange box, the dissolved in the iron, that's what's especially reactive. And that's what gets released under anoxia. So that tends to be high at the sediment surface. So we can go into the sediments and measure that, take these lake sediment cores, section them off at very discrete depths, analyze for all these different fractions of phosphorus. We call that a phosphorus fractionation analysis. So we can actually tell how much is dissolved, how much is bound to iron, how much is already bound to aluminum, calcium. So those things that are bound up in this blue box, we don't really need to worry about them contributing to the internal load. We need to worry about the orange box. We call that the pool of available phosphorus. We can define that. We can do an aluminum application, so we can force that phosphorus from this dissolved in iron form to an aluminum bound form. And then after an application, we can go back in and measure that. And we'll find that now that this line is pretty much straight up and down. We've removed this bulge of available phosphorus at the sediment surface. We've pushed it over here because we now have aluminum, it's now an aluminum bound form, and we've significantly reduced the phosphorus release from that upper layer of redox phosphorus. So that's what we're doing with the aluminum application. So a little bit about the history of alum use. We know a lot about aluminum chemistry. Alum has been around for a long time. It's been used for more than 200 years in drinking water clarification. It's essential in wastewater and drinking water treatment plants today. It was first suggested for use in the water treatment literature, I believe, in 1955. Someone said, hey, this works good in water treatment. Someone should try it in a lake. Took us a little knowledge just a while, but we did the first application in Sweden in 1968. And the first application occurred in North America in 1970 at a lake in Wisconsin. So it's been used in lakes for over 50 years. It's got a long history. We know a lot about how to use it and maximize its effectiveness. We get a lot of questions about safety. Alum is safe. You can buy powdered alum at the grocery store. As a matter of fact, any of you do canning, you add powdered alum to keep your pickles crisp. It's essential in drinking water and wastewater treatment. If you drink water in a large city, it's probably been treated with alum. We use that same drinking water grade alum in lakes. Aluminum chemistry is very well understood. It's predictable. There's nothing black box about using alum in lakes. The dosing is transparent. It's commonly known approach. And it's not toxic. So I wanted to point that out. We're not killing anything with the alum. We're binding up the phosphorus. So in a sense, you're taking away the nutrient source of the algae. You're not directly killing it. Sometimes people confuse it with copper sulfate, which does kill things. This is not copper sulfate, it's aluminum sulfate. It's cost effective. Alum is widely available. There are alum plants nearby most major cities because most major cities use it in drinking water. And because of that, it's relatively inexpensive. It's a highly efficient binding agency, and it's very cost effective because of that high binding efficiency. Most studies that look at the cost effectiveness of alum find that it costs about $70 to bind up a pound of phosphorus. Benefits, there is an immediate clarification. This is a project we did at Spring Lake, Minnesota, where Tad took a picture from the barge the first day we started during an algal bloom, and the last day of application, day 13, you can see that we now have clear water. It's not desirable to do an alum application in high bloom situation, but that was unavoidable in this project. And so we actually had to increase the dose somewhat to compensate for lost binding sites in the flock due to adhering to the algae. So there is this immediate clarification. I always like to point out that that's a secondary benefit. That's not the primary goal of an alum application. We're trying to supply unfilled binding sites to the sediment to have a long-lasting control of internal loading. The clarification of the water column is nice, but not the primary goal. I always tell people if you want to sell your home on the lake, do it a week after the alum application because the water will be its clearest at that point. The real goal is this reduced phosphorus release from the sediments. This is a study at Bald Eagle Lake near Minneapolis, where there was an alum application in May of 2014. In 2011, before the alum application, sediment was sampled at 5 different locations at the lake. Bill was doing this work. He took the sediments back to his lab, and in the lab, he was able to measure the phosphorus release rate under anoxia. Okay, so before alum is the gray bar. You can see how it varied at sites of different depths within the lake. The blue bar is 2017 after the alum was applied. You can see anywhere from 89 to 90 or 86 to 99% reduction in the amount of phosphorus coming off those sediments after it was supplemented with aluminum. So now what is happening here is the phosphorus is down to the aluminum, not the iron. So we're not getting the release rates. We get, in general, I'd say a rule of thumb across our projects, we usually see about a 70 to 90% reduction in water column phosphorus and about that same reduction in chlorophyll, or the amount of algae in the lake, due to the strong relationship between phosphorus and algae. I love this slide. This is Upper Prior Lake, Minnesota. We get an increase in clarity, a reduction in toxins, because as we lower the phosphorus concentration, we shift away from these cyanobacteria that can produce the toxins to a community more dominated by greens and diatoms that don't produce the toxins. But this picture is cool, not only because it shows the change in clarity, but July 2019 was pre-COVID, July 2020 is post-COVID. And if you use your imagination, you might be able to recognize at least some degree of social distancing with the boats strapping themselves together. Where people look for it, this isn't always measured or monitored, but post-Alum application, we generally see an improved fishery. You get clearer water, you get some increase in or improvement in oxygen concentration as you have less organic matter being delivered to the sediments, less organic decomposition. There's more structure and habitat as we get more macrophytes pollinating after the water clarifies. And with that, we're going to move on to this management case study. And I want to emphasize that this is Bill James's and his crew at University of Wisconsin Stout. It's their work, it's their research. The only thing HAB did on this project was apply the alum. We picked this case study. Obviously, we had a number to pick from, but we picked this one because I'm not going to beat your head over. I'm not going to beat you over the head with it. But as we go through this case study, you'll kind of notice the 7 steps. So not only is this a good case study because it shows the potential of alum when it's used in the right situation, but it also shows the careful process that was followed, the diagnostic feasibility, the modeling work that went into this along the way. So Long Lake is, I didn't put that on here, it's near the town of Balsam Lake, Wisconsin. It's a 272 acre lake. It's relatively shallow. It's unstratified, maximum depth of 17 feet, and an average depth of about 11 feet. Bill took a look at the historic water quality. Here we're looking at phosphorus, chlorophyll, or the amount of algae, and the transparency or clarity of the water. And he had data that went back to 93, and he had a data set that went through 2014, some sporadic sampling during those years in the summertime. Over that period, the average total phosphorus concentration in the water column was averaged around 80 micrograms per liter. Average chlorophyll 43, and average Secchi transparency was about 1.8 meters. So it was having some water quality issues and some blooms. So here we are kind of in that defined problem state. Bill plotted the data. This simply plotted total chlorophyll along the x-axis versus, or total phosphorus along the x-axis versus chlorophyll along the y-axis. And what he saw was, as phosphorus increased in general, there is an increase in the amount of algae. This red dot over here is an outlier to that relationship. But it looks like we're seeing some evidence of phosphorus limitation. Probably makes sense to pursue the management of phosphorus as a possible management scenario. He also, in his initial review, started seeing the potential for some internal loading. Although this is an unstratified lake in general, you might argue that there's some weak intermittent stratification occurring in the summertime, although these temperature differences are probably only 2, 3, 4 degrees Celsius. But despite that relatively unstratified water column, still picking up regions of anoxia during the summertime in those bottom waters. So the oxygen demand of the sediment must be high enough that even though there's some mixing going on in the summertime, the demand of those sediments is still pulling oxygen out of that mixed water column. So this is an indication of maybe there's some phosphorus being released from the iron and maybe some internal loading going on. Looked at total phosphorus in 2012 over the summertime. In general, we see a total phosphorus increase during the summer. We see a chlorophyll increase during the summer, and we see a decrease in clarity during the summer. Those can be an indication of internal loading. As the internal loading is occurring during the summertime, we would expect the water column phosphorus concentrations to increase and subsequent increase in the amount of algae. Another indicator of potential internal loading is the watershed to lake area ratio. By the way, when I said I felt like there were 3 pieces of information that were not debatable of being importance in managing a lake, in my opinion, this is one of them. If we know this ratio, which is simply dividing the watershed area by the lake area, that ratio tells us a lot. It's pretty low at Long Lake, and that means that the watershed or the contributing area around the lake is relatively small given the size of the lake. So knowing that, we would understand, we would predict that the watershed load or the external load would have a relatively lower impact on the water column than internal load might. So then Bill went on to do the nutrient budget, the nutrient mass balance. The first thing Bill did was estimate the internal load. We're going to talk about that next, by the way, but he estimated the internal load to be 371 milligrams of phosphorus per square meter per year. He then took that estimated internal load, and like I said, I'm going to tell you how he did it next. But he took that estimated internal load, and that was included in 2 empirical steady state models to estimate the bulk phosphorus loading from the unmeasured external sources. So he did not have a measure of the watershed or the external load, but he backed into that after he knew the internal load, because we need to balance the phosphorus mass. Both of those models that he used, the Nuremberg 1998 and the Canfield-Bachmann 1981 models, estimated very similar external loads, 160 and 176. So I can't remember which one Bill settled in on. I believe it was the Canfield-Bachmann. Really, there's no significant difference between these 2 loading values. And he converted that to pounds per year and was able to estimate 32% of the phosphorus entering the water column at Long Lake on an annual basis came from external sources, and 68 came from the bottom sediments or internal loading. Okay, so that's important. Now we know, or Bill knew, where to focus management strategy. So, for example, if the internal load in this case had only been 10% and external load had been 90%, we probably would not have pursued the use of alum, right? So there's a time and a place for all of these tools. We would have focused the load management more into the watershed. But in this case, this is a high internal load. Pursuing and controlling that load made sense. So how was the internal loading estimated? I talked a little bit about this earlier, but this is in more detail. 6 undisturbed sediment cores were collected. Here they are collecting tubes of mud, if you will, from the deepest portion of Long Lake. They were taken back to the lab. The top 10 centimeters of these cores are then incubated in the dark at 20 degrees Celsius in the lab, okay? And filtered lake water is put on top of them. That's what's showing down here at the bottom, the incubation process. So in some of them, you can see the airline tubes going into the sediment cores. Some of them, half of them, received air. So those simulated aerobic conditions. So it's keeping the dissolved oxygen concentration in the overlying water high. The other ones, he bubbled nitrogen into those, and that forces the oxygen out of the water. So you have anaerobic conditions, no oxygen conditions. So he's simulating anaerobic phosphorus release during the summertime at the bottom of the lake. And then that's what they're doing here with this syringe. They're removing water from the sediment core, and they can measure the phosphorus daily in that. They can look at the change of phosphorus and calculate the rate of phosphorus increase in the overlying water. And that tells us the rate or the flux of phosphorus coming off the sediments. These are the results from that. I'll skip right down here to the table. The anaerobic release rate, he found it to be almost 13 milligrams of phosphorus per square meter of sediment per day. That's pretty high. The other thing he found is this may be counterintuitive or a surprise to some, but aerobic sediments release phosphorus as well. In this case, he measured it to be about 1. So these are the curves. This is how it increased over time in the anaerobic treatment. And this is how the through replicates increased over time in the aerobic replicates. You can see the difference in the slope indicates the difference in phosphorus release. Bill then put out continuous dissolved oxygen data loggers on a buoy suspended at different depths. So he had oxygen recorders at different depths in the lake. And what he found is, so this is recording continuous dissolved oxygen data over the summer. And then what he found is down here at the bottom, if you look at this black line, that's kind of the line of denotation there. At the bottom waters, starting around the beginning of June, they started to lose the oxygen. And that anoxic condition was prevalent in the bottom approximately 4 meters of the lake throughout the summer. So for about 120 days, the bottom 4 meters of the lake was at or near no oxygen. So here's what he did. He assumed that the lake, everything below 4 meters was experiencing anoxia for 120 days during the year. He knew the aerobic phosphorus release, and he knew the area of the lake that was aerobic, everything greater than 4 meters. And he knew the anaerobic phosphorus release from the lab study. He knew the area that was anaerobic for those 120 days, and that's everything deeper than 4 meters. And he just divided that by the entire area of the lake, and that would give him an estimate of the annual phosphorus internal load. So he did that first, calculated that internal load, and then backed into the external or the watershed load using the Bachman-Canfield model. Now Bill had his cool tool, and so he could look at some water quality responses for Long Lake. And what he chose to do is he said, okay, this is our existing condition, about 80 micrograms per liter total phosphorus. And he said, what happens if all that we do is reduce the external load to Long Lake? So that's what this black line is. We start at 80 and we incrementally reduce the external load. So he's turning the knobs on his model. Let's say he reduces the external load by 60%. We go there and he has a predicted total phosphorus concentration of, I don't know, somewhere around 65 micrograms, okay? So you reduce external load by 60%, you improve water column phosphorus from 80 to 60 or 65. But then he said, what happens if we control the internal load by 90%? Well, if we do nothing to the watershed, remember this lake is getting 68% of its phosphorus from the sediments. So if we control that, reduce it by 90%, and we don't do anything to the watershed, we're going to drop the predicted in-lake water column phosphorus down to 39, okay? So this is telling him what the mass balance suggested, is that you get more improvement by focusing your efforts on internal loading control. So if you do the, in this case, Alum application to control the internal load, then the incremental increases or incremental decreases in external phosphorus move along this line. So if you start by dropping it to here and then start working on your external load, you can get the phosphorus even lower. So this all went into his diagnostic feasibility study. He also looked at what the same scenarios, what those effects would be on algae and transparency. So then that went into his plan. He recommended internal phosphorus load control in a 2017 report using aluminum salts, alum. He initiated the next phase of the project, and those objectives were to determine the alum dose, the application strategy, and the cost. So before he went into this next phase, let's kind of review where we were at. He knew that he had 176 pounds coming into Long Lake from external sources every year. He knew he had 371 coming off the bottom, and his model was telling him that if he took a 90% reduction of that, he could get the water column phosphorus down from a current concentration of 80 down to 39. Okay, so he knew a lot here, but what he didn't know is he had not yet defined that pool of available phosphorus in the bottom sediments. And it turns out you need to know that. You need to know how much of that phosphorus is bound to iron before you can do the aluminum dosing. So that's what he did. He did his sediment coring. He determined that pool of available phosphorus. Undisturbed cores were collected from 4 stations, transect along different depths in the lake. He analyzed those in the lab for phosphorus fractionation. So how you did a fractionation analysis, how much is on iron, how much is already on aluminum, how much is on the different forms of organics. They sectioned that cores anywhere from sections of 1 to 2.5 centimeters with the finest resolution in that top 10 centimeters of the sediment where most of the action is occurring. Here's what the sediments were analyzed for. Again, just reviewing, this is the redox P. You throw in the labile fraction of the organic, that's the available. You add all these together, and that's where you're getting the total. This is what he found at the 4 different stations. The purple is the loosely bound or near or already dissolved. The portion that's already, or that is in the iron bound form, and then the portion of the organic that is also available for release. So you can see there was some variation across the different sites. That's mainly because the cores were taken at different depths. You can see there's a high percentage of iron-bound phosphorus in these in the available pool. Different way of looking at that. So as he sectioned these at different depths, so we go from again the 0 being the sediment water interface down to depth of 20 centimeters or 19 centimeters into the lake bed. You can actually look at the different phosphorus fractions at different depths. This iron bound is the red one. You can see it increasing in the top 5 to 6 centimeters, a slight increase in the labile organic, and also a slight increase in the loosely bound fraction of the phosphorus. So you add those together and you get this pool of available phosphorus that I showed on the previous slide, that orange hatched area. So this is the area that needs dosed with aluminum. We want to convert that from loosely bound, iron bound, labile, organic bound to aluminum bound. So it's no longer available for release. Since the water, the bottom water anoxia typically extended to about 15 feet in Long Lake during the summer. The anaerobic sediments below 15 feet are the most likely contributing to the internal loading, okay? So they ended up being the target for the aluminum dose. So the decision was made to treat this, the deepest 89 acres that go anoxic, because that is the greatest likelihood that the iron is going to release the phosphorus. Okay, so the whole lake didn't need treated, just the area that was subjective or that was most likely to have the internal loading. So based on the redox sensitive phosphorus concentration, a dose of 105 grams of aluminum per square meter was calculated. And that dose was determined that it would sequester the available phosphorus in the upper 6 centimeters of sediment located in that 15-foot depth contour. Okay, so remember from the previous slide, most of the action here with the available phosphorus is in the upper 6 centimeters. The lake is going anoxic in that 15-foot depth contour. So we're going to target the upper 6 centimeters in that deepest 89 acres of the lake. To maximize the binding efficiency and the longevity, in this case, the total aluminum dose was split into 3 applications of 60, 25, and 20 grams of aluminum per square meter over with 2 years in between each application. The cost, came up with a cost estimate, the lump sum engineer's estimate to conduct all 3 applications was $337,000. Applications 1 and 2 have been completed. HAB did the application. Here is the map that our application software on our barge spits out. So this is the 89-acre deep water area that received the alum dose. Every individual green line on there is a pass that was made by the barge, 40-foot wide, tracks all that. It's got real-time flow sensors in the plumbing. It's got butterfly valves that can regulate the flow. So as the barge speeds up or slows down, the target dose is maintained. We're very careful about not having gaps in the application and applying a uniform target dose so we don't get any areas that could contribute to the internal load. The June 2018 application was the 60, and the one last year was the 25-gram application. So here are the results. First thing I wanted to show is 2018, 19, and 20. The red is the 2018 application. The red here is the 2020 application. And what we're showing here is that all years were pretty similar in terms of stratification and oxygen zonation. So the results don't appear to be driven by any changes in anoxia at the bottom of the lake. That's important to establish. And then we're looking here at Long Lake, the bottom total phosphorus and dissolved phosphorus concentrations measured, I believe, 1 meter off the bottom. Okay, so prior to the alum application in 2017, you can see this increase during the summertime. That corresponds with when the bottom of the lake went anoxic. So iron release of phosphorus is occurring in 2017. The lake mixes, oxygen is replenished to the sediments, and that load goes down. 2018, so that's post-alum application. 2019, post-alum application. 2020, post-alum application number 2. This is the disadvantage of doing this presentation in a webinar where I can't see anyone, but I'm sure right now we're getting a standing ovation. We don't usually see response curves like this in we don't usually see loading curves like this in Midwestern lakes in agricultural land use settings. So to reduce the release rate or the phosphorus concentration in the bottom water by 80 to 98% is really amazing. So what this is showing is the aluminum is down there. It's binding the phosphorus as it's being released from the iron, and we're not getting the spike in the phosphorus in the bottom waters. So taking a closer look at what's going on, and this is really cool. So Bill went back and he recorded these at 3 different dates after the Alum application. And what we're actually seeing is an evidence of the conversion of the redox P, or that available pool of phosphorus, to the now aluminum bound P. So here we're starting off with a pretty high redox P at the top of the sediments. And then that's decreasing post-alum application to very low concentrations. Okay, everyone with me here? High available phosphorus in the sediments before alum, low after, presumably because the available phosphorus is now bound to aluminum. Well, when those same sediments are analyzed for aluminum, that's what we see. Pre-alum application, low amounts of aluminum-bound phosphorus. Post-alum application, very high, or a significant increase in aluminum-bound phosphorus that corresponds with this decrease in redox P. So this is extremely strong evidence of the conversion of redox P to aluminum-bound phosphorus, which is now reducing internal load into those bottom waters of the lake. And in fact, if we look at, so these, I should explain the graph here, 2012 and 17, pre-alum application, 18, 19, and 20, post-alum application. We're looking at summertime averages. And if we look here at the bottom right panel, we're looking at this lab release of phosphorus, the phosphorus flux study, where we take the samples back into the lab and bubble in nitrogen. When we take samples out of the lake after alum application by 2020, seeing a 97% reduction in the amount of phosphorus coming off of those sediments under anoxic conditions. This is really, really tremendous result. So we've directly reduced that flux of phosphorus from the sediments. And we see that then in the bottom sediments, 97% reduction in the lab. If we actually measure it in the lake, a meter off the bottom, see a 98% reduction comparing to pre-treatment averages. That's for dissolved phosphorus. Total phosphorus is about 82% reduction. And these are right in line with what we typically see after an alum application. So that's resulting, so as we stop that internal loading, we're getting about a 66% reduction in phosphorus in the water column, 70% reduction in the amount of algae, and 80% reduction in the clarity of the water. So these are, this is a tremendous success story. And again, we picked this as a case study, not only to show the potential of supplementing lake sediments with aluminum salt with an alum application, but also as a case study showing how this systematic approach to lake management can be pretty useful. And with that, I'm not quite sure how this is going to work with 200 and some participants, but we're going to try and have a bit of a question and answer session here. I believe Tad's microphone is on and Bill's microphone is also on. So
Great.
I'll defer back to Alana and kind of let you moderate this.
Yep, that's perfect. I have been following the questions that have been put in the chat. So I will ask the questions that I've put in, and then you or Tad or Bill can respond as you guys see fit. So thank you for everyone for putting questions in. Continue to put them in and we will ask all the questions. So one of the first ones here is, how is the timing of the application determined? Is it more effective if it's done in the spring or the fall, or any other things that would determine that?
Good question. The water temperature has to be 42 degrees Fahrenheit or warmer to get good alum flock formation. So that's the kind of the first criteria, is we need to have water above 42 degrees. So that's usually a month and a half or so after ice out, depending on what part of the world you're in. And it can't occur too late in the fall. It has to be above 42 degrees. Beyond that, we prefer not to apply in heavy algal bloom. We feel like we will lose some of the binding site of the flock as it adheres to algae. It also will physically flocculate on the algae, so it's subject to wind drift more. It won't sink as rapidly or where we apply it. So typically alum applications are done in late April, May, and June before the onset of heavy blooms, and also the start of significant thermal stratification. The other popular time is in the fall, after mixing and after the summer bloom has subsided. There's some school of thought, as I'd say is still a little bit preliminary, and that is we're seeing some of these projects being designed to occur in late summer when the lake is still stratified. And the thought there is we might be able to strip out some of that hypolimitic dissolved phosphorus that's accumulated in the bottom waters, in addition to providing flock for future internal loading events. But the short answer, I would say, is spring and fall at this point.
Okay, there's a few questions on the case study you presented, and what is the benefit of breaking that long lake treatment into 3 applications? And why did you decide to do it for 3 consecutive years and not just one treatment at a higher concentration?
Bill, are you available? Well, I'm not hearing Bill, so I'll take a stab at it. There's some thought that multiple applications might increase the longevity, that the characteristics of the flock may stay more reactive. There's some lab studies at least showing that. There are some thought that in situations where we have high sedimentation or potential for burial rate at the bottom of the lake, we do more lower dose, more frequent applications, that we can keep an active layer near the water sediment interface. And the other one, and I don't know if this played in the case at Long Lake, is a lot of times with that initial dose, as you saw at Long Lake, you really get a lot of the internal loading control with that first dose. And so then the subsequent doses are for the longevity. So sometimes it can be a financial reason too, where we can spread the cost of the total application over multiple fiscal years and still get the same benefits from the application.
Great. Another question is, what is the typical length of time that alum treatment will effectively work? Some places say, 7 to 10 years was stated for the amount on their lake, which is a 155-acre lake. Do you have any insight into that?
Absolutely. So an alum application has a lifespan. We are putting, for lack of a better term, unfilled phosphorus binding sites in the bottom of the lake. When those binding sites are full, the flock is no longer binding phosphorus, so it's exhausted. So the faster those bind, so it's a function of 2 things: how many binding sites you put in the lake, it's going to last longer, and how fast those binding sites fill up with either internal loading phosphorus or watershed loading phosphorus. So it will last longer in lakes where the external load is lower, and it will last longer in lakes where the aluminum dose is higher. There was a study done, sorry, on the spot here a little bit, I think For unstratified lakes, you're looking at an average longevity of somewhere around 12 years. And for stratified lakes, maybe somewhere around 18 to 20 years. I know a lot of the lakes we're working on in Minneapolis, they're being designed to last 20 to 25 years. So it really depends on the dose, and it really depends on the loading, how fast those binding sites fill up.
Thank you. What are some lake characteristics that would make it unsuitable for alum treatment?
For traditional alum application, that is what we've been talking about today, and that's to inactivate the sediment phosphorus. Lakes that have high external load are typically not good candidates. You're going to overwhelm those binding sites with external sources of phosphorus, and the control of the internal load is going to be short-lived. So that's another reason to do this nutrient mass balance and understand where that phosphorus is coming from and make sure that you're applying the right tool. There are some cases, we didn't talk about it today, where alum can be used on lakes with high external load. For example, there's a lake that we manage that has very low internal load and high external load from groundwater. And there's really nothing they can do to address the groundwater load. So we just let the lake fill up with high phosphorus water. There's really no other choice. And we go in every 2 years with a very low dose alum application and strip out that accumulated phosphorus from the water column. That's a very different strategy than what we've been talking about today.
And Bill, I see you unmuted yourself. I'm not sure if you have anything to add on any of those past few questions before I go on to the next ones.
Yeah, can you hear me?
Yes.
Oh, good. So yeah, we'll keep going. John did a good job answering those.
Okay, perfect. John, you're the prime guy today. Okay. Next question is, what kind of public use restrictions are there for treated water bodies to have to be in place, like relative to fishing or swimming or drinking when embarking on alum treatments?
That varies. We, HAB Aquatic Solutions, as an alum contractor, we don't have any restrictions. The alum is safe. There's no need to worry about coming in contact with the alum flock after it's applied to the lake. Some lakes choose to close the lake to activity. That's mainly a convenience factor for us. It reduces the boat traffic because we are out there trying to follow an AB line, and you don't have a boat anchored in front of you, or jet skiers zipping around, or people water skiing alongside of you. But other than that, from an environmental or human health issue, there's really no need to restrict use of the lake.
Okay. How effective is alum on shallow lakes? Like we're talking maybe less than 10 feet on average.
Bill, do you want to jump in?
Well, sure. I mean, that's a tough question. It is effective. There are indications that it may not be as effective for certain reasons. But there have been publications that have showed that it's been very effective in shallow lakes. Like one of the issues I think is resuspension. If there's a lot of wave activity, that can resuspend the alum flock a lot. That's not necessarily a bad thing, but it can move the alum to different places. And, we generally want a uniform application. It can also affect the pH if it's resuspended, particularly, during or shortly after the application. But other than that, alum has been used in shallow lakes, and it's increasingly being used in shallow lakes.
Yeah, I agree with Bill. I think one of the considerations with shallow lakes is dosing. The shallow lakes, one of the issues is the sediment, shallow sediment, and therefore the deposited flock could get resuspended, and likely does. But as it gets resuspended, it's also suspending that flock into the water column and pulling some phosphorus out of the water column. So there is some thought that it might actually be more efficient in binding because it's being perhaps more continuously exposed to phosphorus. There's some speculation here, I admit. And it also is keeping the flock at the sediment water interface with this disturbance. So I think one of the things that we need to look at in the shallow lakes is increasing the dose a little bit and trying to compensate or estimate for rapid filling of the binding sites due to increased phosphorus exposure with potential mixing.
Okay, another question that came in was, what parameters do you measure as part of the sediment test? And how many sample sets do you take? Is it based on some sort of spatial metric?
That's a perfect question for Bill.
Okay, Bill, and I think I did mute you because there was some
Okay.
feedback, but yeah, you're good now.
Okay, great. So basically, a lot of this has to do with cost. I try to, consider the deep basin areas in these analyses. Like for instance, with Long Lake, we were concerned that some of the shallow sediments might be contributing as well. So this longitudinal gradient was set up so we could look at that. In other lakes, there might be several basins, different deep basins, and at a minimum, a sample should be collected from each basin. Going up into a depth gradient is probably not necessarily necessary. For instance, let's say the lake is 10 meters deep. Well, I'll collect a sample at 10 meters, 8 meters, 6 meters, 4 meters. That's nice information to have, but it's probably not critical for alum dosing strategies. Basically, that deep basin core is going to tell me the most information. The sectioning is important. The vertical sediment column is very important. I'm looking at this concentration bulge at the surface that's indicative of eutrophic sediments. Usually that occurs because the phosphorus isn't getting buried. It's staying at the top and it's becoming internal load. So I need to know how much of that is, how thick that is, so I can estimate the alum dosage. And at a minimum, for variables, the sediment textural characteristics are important: moisture content, density, and then the phosphorus fractions that are important in internal loading need to be measured: loosely bound phosphorus, iron bound phosphorus, labile organic phosphorus, and just as a side, aluminum bound phosphorus, obviously. So I think that's my answer.
Okay, that sounds good. Okay, another question that came in. How does flushing rate impact lake suitability and longevity of alum treatments? Would a lake with a very high flushing rate be a poor candidate for alum?
It certainly could. It certainly could be. That's getting to that external load question. So if you have a lot coming in, a high flushing rate, I'm assuming that the question is related to a lot coming in, a lot of water coming in, and a lot of water going out. And if that incoming and outgoing water is carrying a lot of phosphorus, we would certainly want to take a look at that load and how it is relative to the internal load, and consider if the alum could intercept that external load well enough to make a difference or not. So that would be a case that would raise a red flag for additional study for sure.
Okay, I got two questions here that are probably for you, John. One is, how many projects do you comfortably manage at the same time? And then how often do you see lakes that you review and then not recommend to do alum treatment?
Comfortably manage. I don't know. 0. I'm not sure if they mean how many applications do we have going on at once. We can do multiple applications at once. We have multiple barges. So I guess I'm not exactly sure what the question is. It's our preference to do them back to back to back and not have our company be at 2 places at once, but we have the personnel and equipment to do it when necessary.
Okay. And then how often do you review watershed and bathymetry and not recommend alum treatment, like a rough estimate?
Oh, I don't know.
I could probably answer that.
Yeah.
Because I usually concentrate on the feasibility studies. There are some instances where I found that I didn't recommend an alum treatment, even though the internal loading was high. That's for 2 reasons. It wasn't mixing into the epilimnia and becoming available. In other words, there was a lot of iron that was bringing it back to the sediment. Under that circumstance, it's really not necessary to do an alum treatment unless the algae are actually directly accessing the hypolimnetic phosphorus by migrating down. So there have been instances where it's not recommended, it's not needed.
Yeah, I would say for me, I would say it's pretty low that by the time people get to me, I mean, they know that we do alum. They've probably been through some kind of an initial screening. So maybe, I don't know, 5-10% of the time, it just doesn't make sense at all. By the time it gets to me. One interesting story though, we did a project. It worked great, water quality, met the goals. There was actually a real estate agent that lived on this lake, and real estate values were going up, demand for the homes. I mean, everything worked as advertised. And there was a lake right next to it. And this lake, obviously, that we did the alum on was a high internal load lake. There was a lake right next to it, within 3/4 of a mile, that invited us over to a homeowners meeting, and they said, we want what XYZ lake has. We want the property value increase. We want the water quality. It's one of those. We want to do what the neighbors did, and no way. They had an extremely high external load. most of the time when I say no or don't recommend the alum, it has to do with external load. And I said, no, I was sorry, that's just not what this is, this wrong tool for the wrong problem. And they got mad at me. I had one of the board members, actually the treasurer of the board, get out the homeowners association's checkbook and started waving it around in the air and said, we have the money to hire you. And, you know, it just wasn't right. And, you know, we have to be honest about that. The worst thing that can happen is to have failures.
Thank you. Another question that came in is, if the flock accumulates at the bottom, would it accumulate to a point where it blocks or buries other biotic constituents? Is that something to worry about?
Could you repeat that? Sorry.
Yep. There's concern that if the flock accumulates at the bottom of the lake, would it accumulate to a point where it blocks or buries any other biotic life in the lake? Is there any concern with that at the bottom?
Good question. Yeah, we get that question a lot. I don't really quite know how to, it's light, fluffy, cotton ball like substance. It's less dense than the sediment, more dense than the water. So it's not forming a solid barrier. Water, biological organisms can easily move through this flock layer. It really becomes dispersed. It gets into the sediment. Remember the space between the sediments we were talking about earlier. It gets incorporated with that loose flocculent sediments at the surface of the lake bottom. And that is good. That helps to kind of solidify it, keep it in place. It also places those binding sites in or near that pore water where the chemistry is happening. So it's certainly not a restrictive barrier. Things, water and organisms can easily pass through it.
Perfect. We have a few more questions and we have a little bit more time, so I'm going to keep going. We had 2 questions come in about carp. So if you have like a high carp population in a lake, is there, should they be worried about that impacting the alum treatment longevity?
I might be able to help with that, John.
Okay.
There have been studies on the effects of carp, and nothing is straightforward. They can have both beneficial and non-beneficial impacts. They can actually be beneficial by stirring the alum into the sediment. That's exactly what we want. We want to expose that alum as quickly as possible to that iron, that redox P, and carp can do that. They can be not so beneficial in that, you know, they're major recyclers. They're sort of a different component that needs to be controlled. I mean, you can control the sediment, but the carp can still, you know, recycle phosphorus through their activities. You know, excretion of soluble phosphorus directly into the water column that cyanobacteria can take up and grow. So even though perhaps sediment phosphorus is controlled, the carp recycled phosphorus isn't. You know, there's a spatial separation there.
Perfect. Thank you. Another question that just came in, does boat traffic need to be limited during and after treatment?
Most of the time, no. I think if we had a very, very shallow lake, we might ask for that. But at least the way we do alum applications, we're actually injecting the liquid alum down below the surface. The flock is forming at a depth, and it's really getting out of the mixing zone pretty rapidly. and sinking very rapidly. So we typically aren't too concerned about redistribution of flock by boat traffic during the application. When we're doing an application, we're going slow. We're a big slow moving object out there. We're not really a collision hazard. So.
Okay, another kind of overview question. Is the goal of alum to bind phosphorus in the sediment or remove phosphorus from the water column, or both?
Generally, from what we've been talking about, the use of alum that we've been talking about today, the primary goal is to bind up that phosphorus in the sediments, that redox P or that iron-bound P. You know, we know we're going to lose some, we're going to remove some phosphorus as it falls through the water column. And matter of fact, you can drive the phosphorus down pretty low with the alum application, but that's not really the primary intention, at least the way the tool is being discussed today. We compensate for that in the dose. To be honest with you, the amount of phosphorus in the water column relative to the amount of phosphorus in the sediments is very low. That's why one of the reasons we get diffusive phosphorus entering our water columns is because this concentration is moving from high to low. So most of the time when we try and compensate for water column loss with the dose, we're only increasing the dose maybe 2 or 3%.
Okay, we have another question about external and internal loads, which you've touched on a little bit, but it might bear repeating again. So for example, if you studied your lake and you know that it's mostly external loading versus internal, like 80% to 20%, is there any value to start with the internal loading first and the use of alum? And if yes, can you kind of elaborate on that?
So that was, the lake had 80% external?
Correct.
Okay. I'm reluctant to make a blanket statement about that situation. I think that goes, sorry to bail on it, but I think that goes back to our 7 steps. I think we would want to know about the timing of that phosphorus delivery over the course of the year. I think there's a lot of details that we would want to examine there. Not speaking specifically to that example, I do know that there are lakes receiving aluminum applications or alum applications prior to complete control of the watershed load. And that's just accepted that maybe it might reduce the longevity a little bit. But we also understand that watershed load control is operating on a much longer time span. And it often takes a longer time and a lot more money to get watershed load under control, especially if it's not point source. So in some of those cases, we're just accepting that and planning for it.
Okay, and this one might be for Bill or you, John. I'm not sure who will be best, but if you guys can answer this, what is the relationship between spraying of weeds and internal loading? Does excessive weed kill increase internal loading?
You're right. That's perfect for Bill. Yeah, that's a tough one too. So the idea is using herbicide to control aquatic plants causes them to die, and they can senesce, and they may release phosphorus, and there could be an algal bloom afterwards. And that could be considered, you know, sort of a manufactured internal load or a human induced internal load. And so I'm sorry, I guess I could say that you could do a budget. You could determine how much phosphorus is in the aquatic plants, and that could give one an indication of, you know, the bulk phosphorus that could potentially be available for release. Aquatic plants are mainly water. they do have a lot of soluble phosphorus that they can release. So this could become available for algal uptake. The impact depends on the density of the aquatic plant beds.
I agree. And what I would add to, I think that this is a research need, in my opinion. I think that the component of sediment phosphorus that we probably understand the least is the organic component. I don't think it's as straightforward as, for example, ion release of phosphorus. Organic phosphorus can be very complex and not break down or release different fractions of the organic, and maybe it gets buried before we even have to worry about it. Or maybe the organic phosphorus is coming off the sediments or out of the sediments at a very different rate, perhaps a very longer rate. To me, it seems like it's probably going to be pH dependent, temperature dependent, maybe even microbial community dependent. And so I don't feel like it's as straightforward as some of the iron aluminum chemistry release and binding. And so how that factors in, to a 20-year lifespan, when you have the release occurring over a much longer period, I think we can learn some things there.
Okay, we have a few questions about inflow waters. So is it effective to use alum into the water of a high phosphorus river, which feeds into a lake? Or have you done projects on treating inflows to lakes?
Yeah, that's a different use than we're talking about today, but alum can be injected into moving water to treat stormwater or stream water, external source of phosphorus entering a lake. It's done a lot in Florida, for example. It's just it's generally a much lower dose to strip that water out of, or to strip the phosphorus out of the moving water. But the idea is you're intercepting it, binding it up before it enters the lake water column for use. That's a whole nother different ball game, I would suggest, and presents a lot more engineering challenges. But it's definitely being done. It's possible, and it's working very effectively in some parts of the world.
Okay, I have one question here on mass balance studies that you presented on in the beginning. And if you have estimated cost for what that would entail for a lake association if they wanted to do a mass balance study. I'm not sure if you have a general quote that you give people, but if you can answer that at all.
I think Bill probably has at least a sense of that.
Yeah, there's no universal price. A lot of it depends on examining the watershed. If it's necessary to gauge streams coming into the lake, that's sort of difficult. That requires expertise and equipment. If there's a need to have automated sampling, perhaps many of you have heard of automated stormwater samplers, that can add to the cost. Ultimately, there's a balance between grant funds and what can be afforded and what ideally needs to be done. I think these studies could range, from $20,000 to $100,000, maybe over 20,000 maybe per year to 100,000 for a 3 to 4 year study.
Yeah, and that was actually a point. I'm glad the listener asked that question. That I meant to bring up. The level of model or mass balance required can vary quite a bit, and I would suggest that the level of sophistication and financial investment probably varies somewhat with the risk and uncertainty. So for example, on Carter Lake in Omaha, that was a $6 million project. That's a lot of risk, and a little bit of uncertainty makes people more uneasy. So there was a lot of work done on that lake. If it's a 1 acre, half acre backyard pond, your risk isn't as high, and you're probably willing to live with more uncertainty. So I think my advice would probably be to start out with something kind of simple with the data you have available, maybe even some watershed loading coefficients based on land use, maybe a desktop model analysis, just kind of play around with it a little bit and see what direction it's taking you, before you invest into a very sophisticated project.
Great, thank you. And with that, we are out of time. Time flies when you're having fun, and this is a good presentation. So I just want to thank you, John and Tad and Bill, for being here, presenting and answering all the questions that kind of came through. As I mentioned early on, I will send a recording out to everyone who registered. And I know there are some questions we were not able to get to, but you can take down the emails that are on this last slide here, and I'm sure they would be happy to follow up with some of the more specific questions that were coming through. So thank you guys for being here and presenting.
Thank you. I appreciate everyone tuning in and for the opportunity, and thanks for setting this up for us. Appreciate it.
No problem. Thanks, everybody, and
All right.
enjoy the rest of your day.
All right.